Okay, can you see the slides? Yes, no, maybe.
Yes.
Okay, good. By the way, I should have asked this before, but when I do drawings like this, you can see, right?
Yeah.
Okay. By the way, yes, all of you can do drawings. Okay, at least some of you noticed during the previous talks. But I of course ask you to refrain from doing drawings during the lecture. Thanks. Okay, so welcome everybody to the last lecture of the series of aspects of higher energy physics. Today I'm going to talk about interpretation and reinterpretation of the analysis, okay? So this was not a talk that was originally part of this series, but this was supposed to be 5 lectures. So I came up with some idea to discuss this aspect that is not actually part of my work, okay? So in slide number 2, if you see, oops, sorry. This is not actually something that I work on. This is more a work for the phenomenologists. I do the experimental physics only. I write code to do the analysis and I take data. So a big disclaimer, I am not that much of an expert on this. Actually, most material in this talk has been adapted with very small modifications from these other talks here, okay? From Kyle Kramer and Nick Wardle. So I know what they're talking about, but it's not something that I usually do. Actually, it's the other way around. The requirements to allow the phenomenologists to do interpretation and reinterpretation is something that imposes requirements on my work, because besides doing the analysis and writing the paper, I have to do more stuff. But it's fine, it's part of the job, and it's something that is going to be useful later. So with those caveats, let me just say one more thing. Reinterpretation won't impose reproducibility needs. What does this mean? The thing is that in the LHC, we do the analysis of our data, and then we publish our results in some way that other people who are not part of the collaborations will be able to use those results to derive conclusions about other kinds of physics. But of course, to validate that, they have to be able to reproduce the official results. So that's what I mean by reinterpretation won't impose reproducibility needs. You may or may not have heard of something called the reproducibility crisis in science. And it's usually something more about biology and psychology results, in the sense that it's very hard for somebody to look at a paper and reproduce the results of that paper. Usually because there are blanks on the description of the experimental methods, experimental materials. Turns out that the data analysis may or may not have been done correctly. There may have been biases, so on and so forth. In our particular case, of course, nobody can go and reproduce the LHC results from scratch. Mainly because there is only one LHC, right? Nobody's going to build a new collider from scratch just to reproduce our paper. There is a limited amount of reproducibility and more on the sense of validation, in the sense that for the two general purpose experiments, Atlas and CMS, there are two. So it would be very odd for one of the experiments to observe something that the other don't. But I'm not going to discuss this further, okay? It's just for you to have this in the back of your mind. If you want to reinterpret results, you should be able to reproduce those results. Okay, so let's start. Let's recall what we learned on the last lecture, okay? So how to do analysis in the LHC in a nutshell. So the LHC gives you a lot of collision events, proton-proton high energy collisions, and you want to filter those events and select a subset which is relevant to test the hypothesis we are considering. By the way, I do physics for search for physics beyond the standard model. So what I'm going to describe here is more or less a search for new physics analysis, okay? A measurement of a standard model parameter is something that is subtly different. As I said, in the previous lesson, it's a bit of an artificial distinction, but it is still relevant. Anyway, let's describe the search for new physics analysis. So I have two hypotheses, the standard model and a new physics model A, which has a free parameter theta A. Now I want to do a hypothesis test. What I have to do is that I have to take this data, design a summary statistic S, which is some sort of quantity which should have some discriminating power in between the two hypotheses. So it should be able to distinguish between them. And I should build a statistical model, P, which is related to the probability of observing this summary statistic given the model A and the parameter theta A, which parameterizes this model. Then you do the hypothesis test and you report your results, you write your paper. And important, you should always publish this statistical model here. It's the equivalent of show your work when you're doing an assignment. It's something that we use it in energy physics to not do, or at least not to do to the extent that we should be doing it. We would describe our statistical method and report the final results, but we would not publish the actual statistical model, the actual likelihoods. So it's this kind of thing here, okay? So you have some data, you have some background, which you may say it's processes from the standard model. So like this. This is one process, this is the other. And you see here that the standard model agrees with the data, while this deviation here that would be true if the model A was true does not agree with the data, so you reject the model. And in a nutshell, that's the end of the story. One comment. Of course, the model has at least one free parameter. And then you don't know which value this parameter takes. So it's really a family of models. I don't understand, Thiago, what do you mean? So before the Higgs was discovered, we didn't know its mass. So the standard model was actually a family of models where the Higgs mass was a free parameter. When you fix the Higgs boson mass, everything else about the model is fixed. So it's a complete description of reality, of elementary particle physics. Another example, you're doing search for new physics, a Z prime model. You could have the measure of the Z prime as a single free parameter. But you would say, oh, it's actually like something like a Z boson. So its spin and its couplings are fixed. It's just a copy, but it's heavier. Now, how do you deal with this? The answer is you consider different values of the parameter, and then you make multiple pairwise hypothesis tests, which means you consider the null hypothesis against the hypothesis that the new physics model is true for a given value of theta A. And then you do this for many values of theta A. And at some point, and when you do this, you're able to invert the hypothesis test and obtain a confidence interval on theta A. And this is all standard statistics. Okay, every statistician just graduated will be able to tell you how to do this. The key thing is that this is easy for one parameter. It becomes complicated if you are in the multidimensional case. So a model where the new particle may have a different spin, different couplings, and different mass. Let's go for a real example here in slide number 5. Okay, and this is historical. Okay, this is actually from 2007, and this is where I started my PhD. So my PhD was searching for Randall-Sundrum gravitons with the LHC data. So I looked at how people did the D0 experiment in Tevatron, searched for RS gravitons. What's the RS graviton? The RS graviton comes from something called the Randall-Sundrum 1 model. I'm sorry, I forgot to put the reference here. And the key thing is that actually has a model for quantum gravity. So it predicts the existence of a new particle called the graviton. So it's the Randall-Sundrum 1 graviton. And there are two free parameters in this model, the mass of this particle and its coupling constant with the standard model particle. So two parameters. And then in this paper here, this zero searched for the proton-antiproton going to graviton, going to both electrons and photons. And these are the results, okay, with one inverse femtobarn. So it was a lot of data at that time, but nowadays it's less than 1% of the data available in the LHC. So let's follow the analysis in a nutshell. What did they choose? What was the summary statistic? So they selected a subset of events which had either two opposite sign electrons or two photons in acceptance. So two of those going into the detector. And of course, when they say electron and photon, they really mean an electron with at least some pt in an eta region, and that has some quality cuts. So an electron which is well identified as an electron, a photon which is well identified as a photon. And then what they did was calculate the invariant mass. So for their statistical model, they made the summary statistic is the number of electrons and photons with invariant mass in a given range. So here they look in a window in this distribution. And then they count, essentially, it's a bit more convoluted than that, but essentially they count the number of events they observe and they compare to the number of expected background events, both from real electrons and photons, so the white histogram here, the transparent histogram here, and in green here you have misidentified events, which are stuff that had an electron or a photon that was not really an electron and a photon. And then you see, sorry, the colors were not that good, but here you see the gray, that there are gray histograms here that represent the effect of a signal. So in gray, you have the total background plus signal. So you would see that here the background looks like this. The data also looks like that. But signal plus background, you would expect a large peak here that you don't observe. But the shape, the size, and the position of this peak are dependent on the mass. The position of the peak is more or less the mass of the graviton, and the size is the coupling constant K tilde. So they do this for a lot of mass and coupling constant hypotheses. And then they start excluding them one by one. Okay, so you exclude this one, let's use a different color here. You exclude this one, you exclude this one. They have a grid and they exclude all of them until there are some that are so heavy or so, and with the shape, with such a small size that they cannot really exclude. And then they connect the dots in a sense, but they find out a region. And this is the inversion of the hypothesis test that is excluded by all of their measurements. In other words, any mass hypothesis here in the green region would have a peak so high in height or so low in invariant mass that it would have been seen on the data. So they don't see and they exclude at 95% confidence level. This 95% confidence level is the alpha of 5%. So the smallish value that they choose to do the exclusion. And then they write a paper and that's it. Now, you may think, okay, but is that the end of it? Then if I want to do another study, I have to start anew? Usually, yes. Usually the experimental collaborations do each analysis separately. Especially because there are different people doing different analysis, of course. And sure, the background samples, for instance, they may be shared. So what's usually done is that you want to, for instance, simulate a background, say Z2 electrons. You have a big background for sample for everybody, and then people apply their selection on that background sample. But the design of the analysis, the design of the cut, the design of the summary statistic, the construction of the statistical model, and the statistics tests are always done separately. And the thing is that then at the end of the day, you have this statistical model, which is great for combinations and studies within model A. If I want to study more Randall-Sundrum graviton, fine, I can keep using this thing. But of course, I cannot use it for a different model because then the statistical model is different. Of course, the efficiency of your cuts, the acceptance of your cuts, the distribution of this thing is going to be completely different. But sometimes it may not necessarily be that much different. Sometimes you have two models that are similar. And that means that the original analysis will also be sensitive to model B. For instance, graviton going to electrons and Z prime going to electrons are not that different. Sure, there are differences. I mean, I will even draw the Feynman diagrams here for us. The graviton has something like this, right? It starts from gluons in the initial state. And the graviton has spin 2. While the Z prime usually has quarks in the initial state, and it has spin 1. And the coupling constants here may be completely different, of course. So it's an initial state, it's a different initial state, it's a different spin, it's a different coupling. There are different numbers of gluons and quarks in your protons and antiprotons. But in the end, it's a heavy particle decaying to 2 electrons. Sure, some distributions of the electrons are going to be different, but in the end, it's 2 high energy electrons going to your detector. So maybe they are not that different at all. Of course, this is a judgment call. This is something that you as a physicist have to study. But assuming that you did it, turns out that maybe the original analysis, the original cuts, the original model that you chose, statistical model that you chose for model A may end up being sensitive for model B. And then you would have some situation like this, where if you were to do the same analysis starting from model B, you would get something like this, and then you would also be able to say, oh, the model B is also rejected. The key thing for you to be able to do that is that you have to capture the definition of this summary statistic S and the event selection, and somehow find a way to reuse or reinterpret existing analysis. And just by the way that I'm writing here, that this picture is, you can see that what you actually need is the prediction for the null hypothesis, so the standard model, and the observation in the data. And with that, you should be able to, quote unquote, put your model B on top and see what happens. By the way, slide 7, I spoke about combination before, and you may be asking, what does combination mean in this sense? And in a given model, you may want to combine different measurements. So for instance, you may combine different channels, assuming a mass for the Higgs boson, all the branching ratios are fixed. But of course, you can do this as a function of a mass of the Higgs boson. So you may search for Higgs to photons, to ZZs, to WWs, to tau, to BB bar, and see if you have hints of the same Higgs boson mass in all of these channels, according to the predictions of the standard model. And this was exactly what was done for the discovery of the Higgs boson. So if you see here, in the green curve means that, I'm not going to explain exactly what local p-value means. Suffice to say that if you have this dip here, it means that you have a signal of a particle with that mass. So the Higgs to gamma-gamma decay all by itself was only 4 sigma of significance. So 4 sigma away from what you would be expecting from a statistical fluctuation. But if you put it together with the Higgs to ZZ, so here in red, and you put it together with the Higgs to WW in blue, the Higgs to tau in purple, and the Higgs to BB bar in light blue, if you combine, if you look at all of these measurements and ask, what's the chance of having a signal in this channel and with the same mass in this channel and with this mass in this channel and so on and so forth. And then you find that the chances are 5 sigma, 1 in something million, 5 sigma away from a statistical fluctuation if it were a Gaussian. And that's the threshold for discovery that we put on ourselves. So that's how we manage to discover the Higgs boson. But this combination has to be done assuming a given model. But assuming in the model, you can do combination between different decay channels, different data sets. So for the Higgs boson, we combined the square root of S, so center of mass energy of 7 TeV and 8 TeV, more or less the same amount of data, 5 and 5 inversely combined. And then, of course, you can combine with 13 TeV. And then you can combine between different colliders. So the lab search for the Higgs, the Tevatron search for the Higgs, the LHC search for the Higgs. How can you see, can you combine measurements from all of them? And in principle, yes, you can. And same even from different kinds of experiments, right? You can combine the data from collider experiments, from telescopes, from anything, as long as you assume the same model. But there is one thing, when you do the combination and you ask, what are the chances of this signal I'm seeing being statistical fluctuation, you have to take into account the statistical uncertainties, which are easy, they are related to the amount of data that you have, and the systematic uncertainties. And those are dependent. Inside the collaboration, it's easy, right? Because all the information is open. You have people in the collaborations that are calculating systematic uncertainties related to identification criteria, trigger efficiency, acceptance, theoretical uncertainties, so on and so forth. But how do you deal when you are not in the collaboration, when you are outside of it? And then you may ask, but why do I care about the outside people? Because the outside people are other physicists, either experimentalists or phenomenologists, that want to know the information, the total information on a model from different data sets, different colliders, different experiments, blah, blah. There are people interested on that model. For some of the big ticket models, for instance, Higgs standard model, Higgs boson, the more usual models of supersymmetry, the collaborations do these calculations themselves inside the collaboration. But we don't do it for every single model that exists. It's obviously impossible. So the people that are interested in this model may want to do it by themselves, but then they would need access to the experimental likelihoods. And you can see that this may be a problem if we, as the people in the collaboration, as members of the collaboration, don't publish these experimental likelihoods. And this comes back to how do we allow people to reuse and reinterpret our results. So here in slide 8, I hope that I have motivated enough that looking at how the experiments present results is a worthwhile endeavor. And this is what people call the LHC results spectrum. And this, again, is stolen shamelessly from Nick Wardle and Pio from this talk here. You can click here and see. On the one side, you have the collaborations do all the work. Take a UV complete model, so absolutely renormalizable, clean model, and do all the work on it. And this has the most assumptions because you are assuming that the real model, so the real physics that describes nature is this model. And then it's easy to use, right? If you want to know, oh, is the mass of the gluino in the PMSSM model of 400 GeV excluded, then you just look at the plot and say yes, no, easy. But then you can start coming to the other direction. Instead of using super complicated models, you can set limits on simplified models. Or instead of assuming a model, you just report on signal strength, amplitudes. So you simply compare how much events you observe with respect to a given model. Or you can take out the observe with respect to a given model and just report how many events you observe, reporting only inclusive cross-sections. And then you can take out the you observe part and say, oh, let's try to undo the effects of the detector in what's called unfolding. And you try to simply give your best guess on how many events of that kind exist. How many so you undo the effects of your efficiency, your acceptance, your systematic uncertainties, so on and so forth. And you can publish the likelihoods themselves, both in the simplified and full likelihoods. I'm going to explain later what they are. There is something called Rihanna and recast, which on top of all of that also automatize the analysis work for you. So you don't even need to do the analysis in your favorite model. You just upload your favorite model to a website, and these guys, here guys is obviously just a word, it's actually a script, run the analysis for you. I like to kid that this is essentially experimental physics as a service. So if one day I get put out of my job, I get fired, it's because I will have been substituted by this thing. And in the limit, you can just release all the data and tell people, here's the data. Do whatever you want with it. And these are some possibilities only, okay? We should always add more possibilities on how the experiments present results. Okay, so let's go through these one by one. Not all of them, and not in all depth, because we don't have time for them. On the extreme case one, you have the collaborations doing all the work in a full UV complete model. So something like the standard model, where you may make measurements of the, it's not allowed regions. You carve regions in the space of parameters, for instance, for the mass of the Higgs and the mass of the top. But those things can also be measured directly in a sense. So you may prefer for something like the standard model to present signal strengths and amplitudes. So how many events do you observe with respect to the expectation? But in principle, you can also do this kind of thing here on the right, where you show excluded or allowed regions for the standard model. Usually we do excluded and allowed regions for beyond standard model models, and usually only for some benchmark scenarios. So here I'm showing, for instance, for supersymmetry, for the HMSSM SUSY scenario, and for the MH125 SUSE scenario that you can click here on the link to see what are these complete scenarios. The minimal supersymmetric standard model has more than 100 free parameters. So what we usually do is that we fix some of these parameters and call these reduced models a scenario. And here you can see, for instance, all of the exclusions that CMS had for the first 36 inverse femtobarn of data. So you can see here that they are more or less complementary, right? You can see that this part here and above is excluded for this analysis here, where Higgs to tau. This part here is excluded by the Higgs to WW. This small part here is excluded from Higgs to tau, sorry, Higgs to TT bar. And this part here to the left is excluded from an analysis of the Higgs boson decay production and decay factors themselves. And then, of course, you could combine all of them. But all of these individually exclude all of these regions. So if you want to ask yourself, oh, the standard, if I look at the MH125 SUSE scenario, is the boson, is the pseudoscalar boson A with mass 500 GeV and tan beta 10 excluded, and then you just come here and read from the plot, and yes, it's excluded. But then again, this brings back the exact question. What if I want to study a model that has a very similar signature? So this particular point is excluded from this analysis, where any of the Higgs bosons in the model decays into tau-tau. What if I want to search for something that also has a Higgs boson-like particle decay into tau-tau? Can this analysis also put limits on that? On the other hand, you can just open the data. You can just release all the raw experimental data and the code to people and say, here, run whatever you want. We don't care. And we do that. You can click here, open data.cern.ch to get the data. But usually there is an embargo period, right? Because we built and ran the experiment, so we want to analyze it with some exclusivity before. But there is already a good amount of data being released. CMS has released half of the data from 2010, 2011, 2012, if I remember correctly. The pro is, of course, that this allows for maximum data preservation, right? Because if you're making it public, obviously people are going to have copies. And well, they have the full data, they have the code, they can do whatever they want. So it's maximum reusability. The cons, of course, is that, well, here I'm just showing a nice picture of an event display, fine. But there are petabytes of data. So it's not something that you can just happily save in your hard drive or your cloud. Actually, in the experiments, we have dedicated clusters for that, dedicated computer farms for that. And not only it's petabytes of data, but to analyze these petabytes of data, we need computer grids. We again need computer farms with thousands of cores. So if people want to do the analysis, they have to bring their own cluster, something which is comparable in magnitude to the worldwide LHC computing grid. In principle, yes, you could rent some computing power at something like Google Cloud or Amazon Web Service, but it would not be cheap. And there is one more thing, that the code that we use to do the analysis and reconstruction is complex. It's complex to install because it's scientific software. It's not something where you just download from the App Store or anything like that. It's complicated to install. It's complicated. It's usually made available as source code, so you have to compile it. And it's gigabytes of source code. So it's also not easy to compile, and it doesn't compile everywhere. This has become a little bit better, that nowadays the experiments also make available virtual machines that are already set up to run the code. But still, it's not trivial to do. And on top of that, I'm sorry to say, but it's code written for physicists by physicists. So it's sometimes not the best written code you have ever seen, or best commented code, but it does the job. One thing that I want to say, however, is that automatizing this part is what those services like Rihanna and Recast are trying to do. And then you have all the intermediate steps. So let's go through them one by one. Thiago, why do you need the full ultraviolet model? Why can't the ultraviolet complete model? Why do you need a full renormalizable model? Can't we do something simpler? So simplified models is exactly that. You assume that only a few particles are relevant to the signature in question. So for instance, if you're searching for dark matter, you may say, I don't need anything to do dark matter. I only need a mediator, which I'm going to call the prime, a dark matter particle, done. So I can simply have a simplified model where I say that I produce the Z prime decays into the dark matter, and there is some recoil. So that this thing recoils against a jet, or against a photon, or against whatever. And this works. Or in the case of supersymmetry, you can say that supersymmetry has a lot of different particles, right? It has to have at least one superpartner for every particle. So gluons have gluinos, quarks have quarks, and the vector bosons have a charge, like the charged vector boson is the W, then neutral vector boson is the V and the photon, and then you have charginos and neutralinos as the supersymmetric partners. And you can say, only these guys are relevant. So you can have a million processes, but let's consider that only the pair production of gluinos, and then the gluinos decay into quarks plus neutralino, or quarks, and then you have this decay, or the chargino, neutralino, or lepton, whatever, decay like this. And then you use the simplified models, and then there are only few parameters that you have to think about. Some of them, again, we do this. We fix some parameters. For instance, in the simplified model, there are 4 parameters: the coupling of the mediator to the quarks, the coupling of the mediator to the dark matter, and the nature of the mediator. So here, let's say we're looking for a vector mediator with spin 1. And then you just have to look at the mass of the dark matter and the mass of the mediator. And then you do the analysis and you find that this excluded region here. This excluded region here. And this works. If your model, the model you're interested in, can be put in this form where only a few particles are relevant, either because the others almost don't couple to the standard model, or they are too heavy, so they're not produced, blah, it works. But sometimes a simplified model is not enough. you may want, because, for instance, one of the things that I am working on right now is a model which has 3 particles, which is a Z prime, a dark Higgs, which is something which is kind of like a Higgs, and the dark matter. And either of these two may decay into the dark matter. So there are 3 particles, and all of them are relevant for the processes I'm interested in. So simplified models is not good enough for me, but it can be good for some models. But what else? Then we continue. Let's keep going to the right. In slide number 12, you can also simply measure signal strength. And this is very common on the Higgs physics results. Why is that? So let's define signal strength. Let's say that the cross-section in a given production mode is what it is, and there is a ratio in between the cross-section that you're interested in and the cross-section predicted from the standard model. And then you will call this the production signal strength. And in the same vein, if you have the branching ratio of your Higgs to a given final state, and that would be predicted by the standard model, and you call this NEF, signal strength of decay. Now, you don't care how many particles are in your new model that gives you this cross-section and this branching ratio. But so it's a weaker assumption, but you're going to assume that only the total rate is modified of this given initial state to this given final state is modified by new physics. So there is still an assumption here, but it's weaker than saying, oh, this is the model, and that these are only the particles that exist. Now you don't, or that are relevant. Now you don't care about the particle content of the model. You just care about these 2 numbers here. And you just care about these 2 numbers here. And you assume this total rate change only. So CMS measures this, and these are the results grouped by production mechanism. And inside of each production mechanism, grouped by decay of the Higgs boson. So gamma gamma, ZZ, WW, everything. And this is what we measure. 1 means that what you observe is exactly the same as in the standard model. And you can see that everything is more or less around 1. Of course, there are some numbers which are extremely different. This one's like 4. But look at the error bars, right? It's 4 plus or minus 2 point something. So if you do the average weight here, you would come to the conclusion that the signal strengths are more or less all close to 1. How do I reinterpret this? First, what I do is that I do the profile likelihood, in which, again, I fix all the nuisance parameters to their best fit values. And I can write it like this. Here I'm writing the log likelihood, but it makes no difference, okay? Because the likelihood is always convex. And then what I do is that I reparameterize this signal strength here as a function of these modifier parameters, coupling modifiers CV and CF, which are related to the coupling of the Higgs to vector particles and the coupling of the Higgs to fermions. And then you can transform this into this. into a measurement, or again, sorry, into an excluded region in the parameter space of CV and CF. A caveat, besides having the measurements, you also need the uncertainties and the correlations in between all of these things, right? This is essentially just a gigantic uncertainty propagation. So to do it right, you know that you need the correlations, but you do it, and you come to the conclusion that these people in this paper here, Sabine Kram, I don't know how to say her name, sorry, Sabine Kram et al., came to the conclusion that CF and CV have a 68% chance of being in this ellipse, 95 of being in this, and 99 point something of being in the third one, 1, 2, 3 sigma. And they compared the results they obtained with the official CMS results, and then they start doing combinations that CMS and Atlas didn't do. And they used this Lilith program here to do it. And then they can use this to set limits on models. Oh, my model says that CV should be something like 1.2. And then CV at 1.2 is already excluded at 95% confidence level. You don't even care what the model is, but it predicts a CV of 1.2, which would somehow modify these things, these measurements of the signal strength. Okay, but still there is an assumption here, right? To assume that only the total rate is changed by the new physics. So all the shapes of the variables, or the shapes of the summary statistic don't change. What if we give up on this assumption? Then you have to simulate the shapes as well. And here we start getting a problem. The problem is that when the experiments do the when the experiments do their analysis, they do detector simulation, detector reconstruction. What they're doing is running the detector. So we in the collaborations, we compare reconstructed real data with reconstructed simulated data. But it's not trivial for somebody who's outside of the collaboration to get reconstructed simulated data. Especially, first because of the description of the detector that you want to simulate is, and then the reconstruction, and then do the reconstruction is hard to do. But even on top of that, running the code, for instance, to simulate the SMS detector takes something like 2-3 minutes per event. And you need hundreds of thousands of events to do an analysis. And hundreds of thousands of minutes is a lot of computer time. Then what we do is try to undo a bit the facts of the detector. Of course, in a sense, reconstruction is a way to get back to the original particles. Remember, what the detector gives us is a signal in a sensor, and we have to reconstruct and correlate to say, oh, this is actually an electron. But this is still a reconstructed electron. And the reconstructed electron may have different kinematics, different characteristics with respect to the original electron. We hope that they are close, but they cannot be exactly the same. So here comes unfolding. Unfolding is when you correct for these smearing effects that the detector gives to you by using some kind of non-parametric estimator. So it's simply a way to undo the detector effects in a sense, okay? So instead of presenting your results in terms of the observed PT or the observed eta, the observed kinematics, we could present the results as if we had the perfect detector, the truth, the detector that is able to see the truth. And technically, how this is done? So this Y is a histogram of your observation. So this is what you actually observe. And lambda, and these are vectors, okay? These, you cannot see here well, but it's bold, is the equivalent mean particle level histogram. So lambda is what you would observe if you were capable of observing the true particles. You had the perfect detector. So what you want to do is that you want to solve this Poisson regression problem, because Y is something that is proportional to K lambda. And this K is the smearing matrix, which is given by something like this. Kij is the probability that a smear being, that a true event in some beam migrates to some other beam. And the efficiency to observe this, an event originating from one of the beams is given by the sum in the observed beams. I'm going to do an explicit example later, but I wanted to have the definition here. By the way, if you do digital signal processing or image processing, and well, even in mathematics, this is what they call the convolution. Okay, I'm now going to say all that I said, but in the terms of the image processing field. Unfolding is essentially the convolution of your image when you know the point source spread. If you know image processing, you know exactly what I said. But now let's go for an example. So here in slide number 14. The thing is that here is a histogram of the unfolded PT of the Higgs boson. For Higgs to be bar, Higgs to gamma gamma, Higgs to ZZ, doesn't matter. The thing is that this is already the answer of the unfolding, okay? When these guys go through the detector, some of the events that are here come here, and here, and here, and here, oops, and here, and here, and here, all the beams. If your detector were perfect, this would not be the case. This would be a diagonal matrix with only ones. There would be no, we call this feed ups and feed downs. But there is smearing, and you have to undo this smearing. Okay. Why don't we always do this? Because this is amazing, right? Here, you remove the need to model the detector to compare to the theory. So here, this AMC at NLO and NLO PS is just the theoretical calculation. So here you are actually able to compare theoretical calculation with data. You don't have to simulate events with your theoretical calculation with those event generators that I discussed in the first and the second lectures. And as a bonus, when you do this convolution, you already unfold the effects of the systematic uncertainties as well. So this is golden. Why don't we always do that? And the answer is that you can imagine that this is, in a way, inverting this matrix. And usually, this is a new condition matrix. It has a very high condition number. So the bottom line is that when you actually want to estimate this lambda, which is what you're interested in, which is this histogram, this histogram as a whole is an example of lambda. This is extremely, extremely sensitive to the fluctuations in the observed data histogram. And then you have to do something called a regularization technique, which works but can introduce bias. There are other caveats that the fact that when you do this inversion, you sometimes you have to assume that these feed ups and feed downs are controlled by some kind of probability distribution, and sometimes things are Gaussian, but sometimes they're not. But if they're not, then you don't know how to solve, so you assume Gaussian, and sometimes the Gaussian approximation sucks. And even worse, and this is new, sure, if it's something that has a particle level interpretation, like the PT of the Higgs, sure, you observe the PT of the Higgs, but there is also real Higgs that has a PT. But if your histogram is some machine learning output, what do you do? And remember that that's what we usually do, right? We histogram the output of the machine learning classificator. What do you do in that case? There is no true level equivalent. There is no true detector to see that, because that quantity is an output that is defined only in terms of your real detector. So there is unfolding. People do unfolding in the collaboration, but it's not the best recommendation because of all of these problems here. By the way, you may be asking yourselves that Thiago, okay, but it's either an invertible matrix or not. Consider that this problem is mathematically equivalent to the following problem. Imagine that you have a temperature distribution in a room or a solid, whatever, doesn't matter. An initial temperature distribution, and then time passes, and you have a final temperature distribution. Sure, it's a differential equation, so there's uniqueness, right? The final temperature distribution is uniquely related to an initial distribution, and vice versa. But how well do you have to measure your final distribution to be able to undo the process numerically and get back to the initial distribution? And the answer is it has to be perfect, or else the distributions may look a lot alike. And we obviously don't have perfect measurements. So then you see it's problematic. The temperature in my room right now is something like 18 degrees. Can you actually do the deconvolution and tell me what was the temperature at midnight? No, right? Okay, so unfolding is good, but there are problems. What else? And here comes the need to publish the likelihoods. So let me give you just a small refresher on likelihood. I spoke a bit about the probability model, so let's refresh it a bit. A probability model is the probability of observing X data given theta parameters of the model. And then you have the data X0 that you actually observe. What's the likelihood function? The likelihood function is a function of only the theta parameter because its value is given by this probability model evaluated on the data that you actually observed. So here you already substituted these arguments. It's only a function of theta. Notice that then the likelihood itself doesn't describe any distribution of X, of the data that you observe. So the likelihood by itself, it doesn't have enough information to generate more data. You really need, and you need to do that to do most of statistical procedures if you want to do frequentist frequentist statistics. But usually when people in high energy physics say likelihood, they really mean the whole thing. So both this model and the data and the observed data. I'm sorry, but that's how it is, okay? And yes. Fine. With this caveat, what's the general form for this experimental likelihood? So let's make a distinction here. All of those theta parameters are identical for nature, right? They are all parameters of the likelihood. But I'm interested in some of them, like the mass of this new hypothetical particle, or the cross-section for my new process, and some of them are nuisance. I don't really care what they are. I don't know what they are, but really, do I care? Do I care about the temperature of the real temperature in my detector? No, it's something around, I don't know, minus 70 degrees. But do I really care if it's 71 or minus 71 or minus 70.5? No. So what we do this change, we do the separation between parameters of interest and nuisance parameters. So what we usually do is that we profile the likelihood and the likelihood ratio such that in the end we only have one parameter of interest, me, which is some common multiplier for the signal yield. So me equal 1 is what I expect for the signal that I'm interested in. Me equals 0 is the fact that the signal that I want is not there. So this is, by the way, completely analogous to the signal strength that I just discussed previously. And then I have to sum over the signal and background contributions. So this is the probability, these are the number of events that I observe, and these are the expected number of events that I expect. And this is me, which is this common multiplier, all the signal events from all sources that I expect, plus all the background events that I expect. And then the nuisance parameters may change these numbers here. And when I sum over all signals and all backgrounds, I have this form here. And then this sum is this number of events that appears here. What else do we need? We need the form of this probability, and if it's a histogram, then it's a binned likelihood, and then you have a product of all of these bins in the histogram. So what are the probability that I observe 5 events in the first bin, 7 events in the second bin, 8 events in the third bin, so on and so forth. So it's the product of all these probabilities. And since it's bins in a histogram, it's Poisson probabilities. So here is the form of it. And remember from Bayes' theorem, you cannot forget the probabilities for the nuisance parameters. In Bayesian statistics, you would call these priors, okay? But here is just the probability distribution for these nuisance parameters that I measure in situ. What does it mean? It means that in my measurements, I go and actually do measurements of the nuisance parameters with some uncertainty, with some confidence interval. And then I assume some form of probability distribution for them. Thiago, this is complicated. Example. Let's do an example search for new physics, okay? So this is what looks like a typical search for a new physics signature. Let's say that there is a single source of background. So it's this blue histogram here. You can think of this as the sum of all backgrounds, it doesn't matter. And I'm not even saying what is this variable here, just that it's distributed like this. And then blue is the nominal background and red is the new physics signal. And the black part, the X points in black are the observed data. And I'm going to divide the data into 3 regions. Let's say this is one variable, could be, for instance, missing transverse momentum. And there are 3 categories: low, medium, and high purity. Why do I do that? Because you can see that here on the right, there is less signal. But the ratio, there is also less background. So here, the ratio signal over background is larger. So this category is more pure. While here I have more signal, but there is a lots more background. Oh, Thiago, so why don't you keep only the right one? Or maybe why don't you keep the left one? And the answer is exactly what I said, that different channels. It's stronger if you do the statistical combination of the 3. You have better results. So we have 3 categories: low, medium, and high purity. And then each category, the histogram has 30 beams. Now, uncertainties, yes. Let's say that there are 2 uncertainties on this background. For instance, there is an efficiency and a scale factor. What does this even mean, Thiago? Let's say that the efficiency is the fact that you don't know exactly the efficiency of your selection. So there is an uncertainty on that. And on top of that, when you actually calculate the efficiency, you are calculating the efficiency on simulated data. But there may be a difference in between simulated data and real data. So you have to do a correction for that. So bottom line, this background can fluctuate up and down by 2 constant factors, which are independent. And then each beam has an uncertainty, an additional uncertainty that is uncorrelated between beams. So each beam also has an uncertainty that fluctuates up and down. For instance, because your simulation has a finite size, so there are statistical fluctuations on the simulated data. And they are independent beam by beam. So each beam has this extra uncertainty. And then there are 2 uncertainties in slide number 19, which are correlated in between the beams. For instance, scale n, energy scale, and fury. Energy scale, suppose that your measurement is badly calibrated. It's always badly calibrated, but the calibration is never perfect. But when you do the calibration, there's an uncertainty. So maybe all of the distribution changes in a coherent way. For instance, beams here in the left could fluctuate down, while beams here fluctuate up because of this energy scale miscalibration. And then there's some theory uncertainty that, for instance, the calculation you did was only leading order or only next leading order. Of course, there is always something like that. And then it makes the beams go here in the left go up and the beams on the right go down. So there is a correlation. So how many parameters we have? And then we can count. We have the 2 scale uncertainties, 90. We have 90 beams, and each of them has an independent uncertainty because of the simulated yields. Right here in slide number 18, each beam has an uncertainty. There are 90 beams. And then the 2 uncertainties that are correlated. So in total, we have 94 nuisance parameters. And this is absolutely reasonable, right? I mean, the histogram with 30 beans and three categories. This is absolutely normal. But notice that 94 nuisance parameters, I'm coming back here. This means that this delta here is a 94-dimensional vector. And yes, there will be 94 times 94 matrices involved. So here we start seeing that the size of the problem we have. But okay, 94 nuisance parameters. Now, let's try to tame this beast for a second. Let's write the number of background events in a given bean as a fraction of the events in that bean multiplied by the total number of events, okay? Like this. And then this delta are the 94 nuisance parameters. So remember, there are uncertainties on the normalization, right? So uncertainties on the normalization, it's usually 1, right? Usually, if you got the exact number, you multiply by 1, but it may fluctuate a bit up or down. And usually this will follow a log normal distribution. Log normal distribution is the distribution of a variable which the logarithm of that variable follows a normal. And then this log normal distribution is always positive, and it's usually centered at 1. So you parameterize the normalization uncertainties like this. The bean by bean uncertainties, again, is the same thing. The number of counts in a bean is always a positive number. Almost always a positive number. So if you got it exactly right, it goes up and down. But if you got it exactly right, it's 1. But it's something like can be 90%, can be 110%. So again, log normals. And these are the size and the direction of the uncertainty. So if it's positive, it fluctuates up. If it's negative, it fluctuates down. If it's 0, you got it right. The correlated systematic uncertainties, as you can imagine, are a pain. What we actually do is that we calculate these are what we call shape uncertainties. So let's come. No, I don't think I need to come back. You can imagine that the true histogram has a shape like this, but because of the energy scale, you may have a shape that is like this. If the energy scale is above what you thought it were, or like this, if the shape scale is under what you thought it was. If the energy scale is under what you thought it was. So what you do is that you interpolate the shapes, and then you interpolate it quadratically. But these are alternate shapes. They are usually 1 sigma fluctuations. So you measure your energy scale is something like 1 plus or minus 0.1. But it may fluctuate. It may fluctuate above and beyond 1 sigma. So what you also have to extrapolate. And then extrapolating is a dangerous business, right? So to extrapolate, you do linear extrapolation. So bottom line, what you do is that you write these functions here in this form, where these pi parameters are actually functions of this form here, where here in the middle, for 1 sigma fluctuations, you have this quadratic interpolation, and above and beyond one and minus plus 1 and minus 1 sigma, you have the linear extrapolations. And then, of course, you have to match, make sure that the things are continuous and have the continuous derivative. I'm, of course, not going to derive all this, but this is what's happening here. And then you have the parameters that you need to write these functions. So when all is said and done, in slide number 22, you can write the likelihood for the search like this. Where here you already factored out the scale uncertainties and this number of background events that go in each beam have all these forms that I just said. Thiago, why the hell did it went through all of these? Because if you now I have written it in a general form, which means that now I only need to publish these coefficients here to publish the full likelihood. Now it's just a bunch of numbers. And I can write it in a standard, plain, human readable format. It's just a text file. This is what we should be publishing. This is what we are publishing now. But wait, back up a second here. How many terms are here again? 729. It's 90 observations here, 90 expected signal yields, and then you have 9 normalization terms because you have 1 term per category, and then you have the 2 normalizations. The correlation uncertainties are monstrous because it's 450 terms. You have 90 functions, 1 per beam, and each of them is 1 plus 4, 5 quantities to specify to go and look back at the forms. And then more 90 terms for the uncorrelated uncertainties. And this is a simplified analysis, okay? This is 30 beams, 3 categories, and 2 uncertainties, 2 uncorrelated uncertainties and 2 correlated uncertainties. You can see that the correlated uncertainties are the problem. Wow. What do you think happens when you have 30 signal regions, each of them has 100 beams, and you'll have something like 20 or 30 correlated uncertainties? For instance, when you are doing the full likelihood combination of the Atlas and CMS experiments for the Higgs boson. Yes, it blows up. What's the solution? Simplified likelihoods. And the key thing here is that all of these components of the systematic uncertainties, they are actually independent of each other. One thing comes from uncertainties in the simulation because of the limit finite size of the simulated samples. One comes from theory, one comes from luminosity, one comes from energy scale. They're all independent. So there is this nice paper here by Andy Buckley et al. That proves that with that knowledge that the components are independent, and assuming that the central limit theorem is true, we can write something called the simplified likelihood in this form here. And then this A, B, C, and rho parameters that appear in this simplified likelihood, they have some very nice analytical expressions as a function of the variance and the skew of each elementary nuisance parameter. But the key thing is that you can actually deduce them from the three first moments of the event yield distribution. So from the number of events that you expect in each beam. You calculate the average, the variance, and the skew, the third momentum of each beam. And then they show that if you have P beams and Q nuisance parameters, the number of inputs that you need for the full likelihood goes like 2 times the number of nuisance parameters. But it's constant for the simplified likelihood because it's this expression here. On the other hand, of course, if you want to do the simplified likelihood, it can be shown that it goes quadratically with the number of beams. So it's a trade-off. Do you have more beams or more nuisance parameters in your experiment? Depends on the analysis. But the experiments may want to publish both, either the simplified or the full likelihood. And then people that want to reuse these data, these results, choose one of them. Now, with the full or simplified likelihood, you can simply describe the experimental analysis results by what you predicted for the null hypothesis, so what's your background, what's your data, and a set of likelihood patches that describe the alternate hypothesis. You just have this part here, this number of events in each beam for your signal. And then you should, if you as a theorist or a phenomenologist are interested on this, on using the results of a given analysis to put limits on to study your model, you simply write a likelihood patch for your model, which mostly translates to finding out the distribution of the variables used in the experimental analysis for your model. There is still an issue that you have to do signal sample simulation, but at this level, you don't really need the full simulation. You can do the parameterized simulation, for instance, with Delphis, that I have talked about in the second lecture. And it's already happening, okay? So for instance, for this Atlas paper here, there are additional resources available in the HEP database, including here the archive of full likelihoods in a standard format. So it's now happening. The tools of the trade, besides the repositories of data and simulation and likelihoods, so HEP data and CERN open data, there are plenty of tools that try to simplify and automatize this process if you want to reuse your some experimental analysis for your signal, for your model. Some of them are specialized for supersymmetry, like as Model S. Some of them are specialized for Higgs boson. Some of them are completely generic, like Recast. Some of them even use the results not only from Collider, but also from many other experiments like telescopes and the dark matter detectors like Checkmate. And for this, I invite you to look at the full paper here. That is the bibliography of this lecture. So this concludes the lecture, and now let me spend some time about the hydrogen physics as a whole. So high energy physics is, in my humble opinion, the most fundamental field of science. Sure, of course, there is math, but math is not science. Math is art. If you want to go to science, if you want to go to compare with nature, it's high energy physics. And from which, of course, there are all the other fields, but if you believe in reductionism, you could get all of the physics, all of the chemistry, all of the biology, all of the psychology, all of the sociology, everything. But of course, this is just a dumb high energy physicist dream. But the key thing is that here we are studying the smallest building blocks of matter. And this field is powered by contributions from people doing theory, people doing experiments, computer scientists that actually help us with all of this code, engineers to go and build the detector. And we have to cooperate to move this field forward. In the theoretical side, we have had this resounding success with the standard model. I showed you in the first lecture that we are able to do predictions that are better than 1 part in a billion and get it right. But the story continues to unfold. There are still extensions from the standard model which explore new ideas and address the data that comes from other fields, like astronomy, cosmology, for instance, dark matter. From the experimental side, because of the size of the apparatuses that we need to do our studies, the field has moved to global collaborations that design, build, and operate extremely large and complex detectors. The CMS detector itself was built by a collaboration with 3,000 people. And as I said, it's petabytes of data. And by the end of the LHC era, we're going to have at least an exabyte of data. So it's gigantic data sets. And we need a lot of resources, both people to work on it and computer power and disks, tape, network. And this is allowing us to measure the properties of the particles and fields that make these smallest building blocks of matter to unprecedented precision. So now I'm not going to have false modesty. We're doing an amazing job. But the key thing is that it's a long-term endeavor. The LHC was first proposed in 1989. I was 6 years old. And if all of you are undergrad students, I think none of you were born yet. The experiment time scales are measured in decades. Right now we have to prepare for the challenges ahead. We are preparing, designing, and building new experiments all around the world. The LHC itself is scheduled to run at least until 2035. The next collider, the so-called future circular collider that the CERN is proposing, is something that is supposed to work until 2070, 50 years from now. I think that the people that are going to be working on that collider have not been born yet. So it's humongous in every word, in every sense of the word. So now here, I would like to thank all of you for paying attention to me, for listening to these lectures, and most importantly, I want to tell, we need you, okay? We need people to keep moving this field forward. We really need, because the time scales are decades. We cannot afford to stop doing it for a while. We really need the people now to come and work with us and work with me. And with that, that's the end of the lecture. Thank you very much. And please join us. You can see here the website. Okay, thank you very much. I will look at the questions now. That if there were questions on the chat. So first, there was a question about from Daniel Moraes. So the existence of gravitons was proven. I thought it was a hypothetical particle. Sorry, so my explanation was not good. No, the existence of gravitons was not proven. That was the job of that paper that I showed. So these guys here, these people here, wanted to see if the graviton existed. Turns out that the graviton, this particular kind of graviton, the RS1 graviton, does not exist if its mass and coupling pair are in this green region here. And this is an old plot. Nowadays, there are better exclusion limits. So yes, as of now, it's hypothetical, but that just means we have to search for it. I also searched for it, but with the LHC data. So I did not find any graviton there, okay? Okay, there are more questions here. Let me see. Thiago, you shared the slides presentation somewhere. Yes, they are going to be on the website of the school. What else? What else? What else? Thank you. Yes. Okay. Yes, it's extremely tiring work, but it also has its perks, right? I mean, it's tiring work on the same sense that, I don't know, working at Tesla and sending rockets to Mars is tiring work, but it's, you know, it's something that warms my heart. What is the importance of hypothetical particles for HAP? So it's the other way around. We don't know which particles are hypothetical. That's the thing. We think we have a model that describes nature, but we are not sure. So we have alternative models. Maybe it's not like we think it is. So how do we know what it is? We make hypotheses and test those hypotheses. That's the scientific method, right? Try to falsify hypotheses. Of course, the standard model is amazing, but it cannot be the end of the story. Because as it was said before, at the very least, it has no gravity. So something else has to give. More questions, feel free to raise your hands or to just speak at this point. Okay, so thank you very much again. I'm going to tell you something. I have everybody's email, okay? So I'm going to send you one and only one email, again, with the links of all the slides, of all the talks, except the first, sorry. And inviting you to know our group better. And from that email, if you want and are interested in learning more and maybe coming and working with us, I will feel free to reply and then come in contact with me if you want to have a working experience in high energy physics. Okay, I think this is it. And yes, we have spots, we have jobs. Nós temos vagas, por favor, venham. Okay, so I stop recording now.